All right, welcome to Module 3. So here is the first part of actually the hands-on things that we're going to be doing. Not so much research. So we're going to be getting started with pre-processing. And so we're pretty lucky when it comes to Landsat 8. Pretty much everything that we get, it has already been pre-processed. So what we're downloading, this level 1 data, it's all pre-processed for us. So we get to skip this step, but I'm going to make you do one thing anyways, and possibly a second one. So as we work through this pre-processing, there's some very technical data. It's a lot about calibration. It's a lot about georeferencing. It's really like getting your image to be on the ground as it's supposed to be. So the first objective is managing image channels to create composites for the enhancement of information found in an image. Well, I'm going to be getting right to that, but I want to go through the image processing steps because what I'm talking about here, this first objective, doesn't actually dive into processing yet. It is really just how do you view your own image. So this module is the pre-processing module. And well, it's half of it anyways. So pre-processing, we're looking at radiometric calibration and we're looking at geometric correction. So radiometric calibration, we're looking at getting the satellite data to be giving me actual numbers from the ground in a physical unit, rather than just being a digital number and just a scaled value and going from there. So that's the radiometric calibration. We're going to talk about that. That's why when you look at the values for your Landsat 8 data, it is all very large numbers because it's actually put into an energy value. Geometric correction is looking at the georeferencing. So the geometric correction is the next module. We'll be getting into that. Then the second step in processing is processing and analysis, and that one is the transformations and mathematical analysis. So this is where I'm actually making changes to the actual data itself. So I take an image and I do some math with it and I come up with a new image entirely. That new image has new values to it and shows more information that comes out of it. We are going to be doing a few of these and a little bit of mathematical analysis with it, and then working from there. Then we're going to go into post-processing. So post-processing is looking at classification and change detection. This is how do I group my data in ways or display my data in ways that it can be read so that the client can make decisions. So it might be like thematic work, it might be actual numerical values with samples and so forth. So that's the post-processing side. Last but not least is presentation. Like I said, remote sensing is an art. So how do you display this information? Do you write a report? Do you do a chart? Do you just give them images? Are you giving them tables of information, etc.? So you're going to, in this class, you're going to actually get your hands on pretty much everything in this list. There's of course more that you can add to it, but that's just the starting point. So I'm going to jump back into the objective itself, which is looking at composites. So a composite is how we actually represent our bands onto a computer screen. So a composite itself is actually color. It becomes color. If we were to look at a computer screen, it works in red, green, blue. So RGB is how the computer screen projects its numbers. So you can think of R as like one slot, G is a second slot, and B is a third slot. Each of these slots, no matter what I put into the slot, it is going to represent it as the color that it says. So for example, I could take like a band 9, and I'm going to put band 9 in R. Now, R represents red, so all of band 9 is going to show up as red. If there's no red, it's going to be black. If it is really high values, then it's going to show up as really red. It's the same with green. So if I have low values, it's going to show up as black. If I have really high values, it's going to be really green, and then there's that transition in between. Same with blue. So whatever I want to show that band as is the color that it's going to show up as, and that's the slot I put it into. So we have digital numbers, 0 to 255. What a digital number is a scaled value that is based on a color theory called the color cube. And so it's like a three-dimensional representation of color. That is kind of your coordinate. The way this works is almost like a layered coordinate system where R is like your x-axis and G is your y-axis and B is your z-axis. If that helps you visualize it as well, that's perfect. So 0 to 255, 0 is a black pixel, 255 is a white pixel. That means black means it received absolutely no energy, or it has exceeded, or not exceeded, but been below the minimum amount of energy it requires to say, yes, this is an energy pixel. On the white side, it has hit the maximum. Now that means that it could be much higher. The actual energy levels could be higher, but it maxes out at 255. So that's the digital numbers. So going down here into natural or true number or true color, this is what our eyes can see. So this is how we view the world. So if I use this as an example, looking down here, I've got a little table. So I have my satellite band, and then I have the display that goes on the screen. So if I'm using a natural color, I'm going to put in the colors that represent the display. So my red band from the satellite is going to go into my red slot. The green band is going to go into the green slot. The blue band is going to go into the blue slot. Now because the colors actually match, it's going to appear as natural color. Sometimes it's very deceiving because you're like, no, it doesn't look like that. But that's because perhaps the satellite band is actually in a different location in that wavelength on the electromagnetic spectrum than the actual display. And you'll notice that as well if you're looking at a color on two different computer screens from two different companies, or even two different versions of the same screen. That display is going to look different, and that's just really the way that the computer screens are built. And it also helps us with printing as well. So if we need to display it, that's what it's going to do. So this means, again, that the colors are going to naturally match. Now, there are some bands that don't have a color. Like, for example, shortwave infrared. What color is that? It doesn't have a color. So we call this a false color. And so we take, like, for example, our near infrared, and we make it a red. And then maybe we'll take shortwave infrared, and we'll make it green. And then we'll take the red band, and we'll color it blue. Why not? You can choose whatever you like. There are some standards, like there's and I'll get to this in the next slide, but there's like 743, there's the natural composite, which is like 321, and it changes based on the different satellites. So whatever bands that satellite has, it has something called channels. And so let's move over here to this one. So a channel is the slot in the database associated with the number. So like, what are you talking about, Karina? So Landsat 7. I'm doing this because on your assignment, you got to look up Landsat 8. Haha. So Landsat 7, we have channel 1. Channel 1 happens to be in the blue part of the electromagnetic spectrum. If I say channel 4 in Landsat 7, I have to look up the near infrared in, the near infrared is that it falls into that slot, right? So that's the slot. So band 6 is thermal. There's my thermal energy that goes into the 6th channel. So it's kind of like a TV, right? Where you say, I'm going to go on to channel 4. Well, channel 4 here is near infrared. So I would look at channel 4, and that's all I can look at one time is that one channel. And that is normally what we would do. Because I have 8 bands. I can only use 3 to create color, but if I look at one, it's just going to be grayscale. So it's just 0 to 255 all the time. So with this, now I can associate the channel number with my composite. And this makes things much easier. So if you are able to remember things based on the channel number rather than the actual colors and names, it actually makes the composites easier to remember because people really get confused when suddenly I'm putting my red band in the blue slot, right, for the channel. So like for example, Landsat 7, we have a natural composite of RGB. So we have red, which is 3, band 3. So it goes in there. Band 2 is green, and band 1 is blue. And so we put RGB, so it's 321. So the channels that I'm using is 321. False color can be anything. If it is not 321 for Landsat 7, it is a false color. That could be anything, but this is a standard that we use in forestry. So using that as in my example, you can go into Envy and just like create colors. And you can say, okay, I'm going to put this band and this band and this band, and choose them all differently, and then come up with your own idea. And you're like, hey, that looks different. Hey, look at what that shows me. Wow, look at that one. So it gives you a very different perspective of your images. So that kind of comes down to color theories as well. So we have 3 colors. We have red, green, and blue. So we can either have a subtractive color or we can have additive. With light, we have additive color. So we have red, green, blue. And then if we add like red and blue together, we get magenta. If we add blue and green together, we get our cyan. And then we add green and red together, we get yellow. If we add all of those together, we get white. So that is all the wavelengths all together is white. On the other hand, we have subtractive color. So if we have yellow, magenta, and cyan, that's the starting point. Then we have, if we add together cyan and yellow, we get green. If we add together yellow and magenta, we get red. And if we go magenta and cyan, we get blue. If we add all that together, we get black. This is how pigment works. This is how printers work. So if you go out and buy a printer, you're probably going to get a CMYK printer, which is cyan, magenta, yellow, and black. So that's where that comes from. So in color theory, we're dealing with light. That's how the computer screens work with. They do end up transferring into subtractive if you have to print them. But otherwise, the additive colors is what we're working with. And then you can come up with all kinds of colors like orange, teal, turquoise, and all kinds of fun things to do. Pink, which is like really actually a light red. So moving into the next objective is looking at contrast enhancement. But what's first most important to see is the spectral signatures. Now this is really important because it really shows us what is contrast. So spectral signatures use something called reflectance, and reflectance is a ratio of reflected energy over the original energy that was received multiplied by 100, and so that gives us a percentage. So it's a line graph. Spectral signatures is a line graph, and it represents the reflectance of each wave, and so this is what they look like. So I have 3 examples here, and yes, you need to know them. You need to be able to identify them when you are looking at them. So we can see water only shows in the red, green, blue spectrum. Once it hits near infrared, it disappears. It doesn't reflect at all. It gets all absorbed. If we're looking at green vegetation, we have a peak in the green. That's where this peak sits. And then it goes down in the red. And then look at what it does in near infrared. Did you have any idea how much of a difference that we are seeing for green vegetation in something that we cannot see? So this means that I can really truly identify my healthy vegetation by looking at near infrared. And so if I'm going to compare green and near infrared, look at that difference. If I want to compare red and near infrared, look at that. So this is going to help me identify. As it says below, chlorophyll absorbs red to run photosynthesis. So we can see that that's why it dips down. And that's why there's not much reflectance in the red spectrum, is because it's using red to do photosynthesis. Then we have mesophyll, which is the structure of the plant, and that reflects near infrared, so that is what's happening here. So we can see how much of a difference that makes. Now, as it is not green, so let's say the winter is coming, the red starts to lift up a little bit. and then the near infrared starts to go down. Why? Because there's not as much photosynthesis as the leaves are dying. So the red, it doesn't absorb red, so it's actually starting to reflect more. And the mesophyll, which is the structure of the cell, is starting to die off as well. So it starts to go down as well. So you're going to start seeing this curve to smooth out a little bit there. Then we got soil, which looks kind of like a logarithmic curve. It looks a little bit flatter in this case, but it's kind of like a logarithmic curve. You can see how the in the higher near infrared, or not near infrareds, but the higher infrareds, it pretty much flattens out, and then it's much lower in the visible light spectrum. So in visible light, if you have brown soil, brown dry soil, it's sitting here. If you have wet soil, this drops down because now you've got water involved. So those are three important ones. You do need to know them, like I said. Now, if I was looking for contrast enhancement, which band would be the best band? So looking here, they're all pretty similar, right? And if we hit the red, they're all kind of like even more so almost the exact same. So I wouldn't really be able to tell much difference between water and so, or not so much soil, but water and green vegetation, or soil and green vegetation. They're all going to look the same. I'm going to get the same digital numbers back. So what I'm going to do, let's see if I go into the near infrared spectrum. I have 0 for water. Then soil has a big gap, and then between the water and the soil as well, and then the green and vegetation. There's a big gap between them. That means my contrast is going to be very high. So if I'm trying to identify between the three of them, I might choose the near infrared. So that just because of the nature that I can actually see more from that. So that's spectral signatures, and moving on to contrast enhancement. So I want to clarify between these two words. So there is a contrast enhancement, and then there is transformations. And people always get this confused, and this always ends up on an exam. I always ask this on exams, and people get confused so much. So I want to clarify this. Enhancement is like makeup. So makeup can be applied. It can be done up really well. You can like completely change the look of somebody by wearing makeup. But all you need to do at the end of the day is just take a cloth and wipe it off. A transformation means you're actually physically changing that person. So this would be like a plastic surgery or something. So a transformation is that really you're not going to be able to change back. Now, of course, I don't have a way of really giving an example of this, but let's say a transformation for an image. If I do a transformation, I'm still going to have the original data because there's always backups of that. But the next step creates a totally different image that I can't, it would take a lot of math for me to go backwards. Where an enhancement, I can just click and it's gone, right? So makeup is really easy to take off. Transformation, it's a lot more challenging to try to change back. So we are looking at enhancements right now. We'll look at transformations later. So there are several techniques in contrast enhancement. So all the stuff that I'm going to talk about here is for one single band at a time. I don't want you guys thinking it's for three of them. I know that the NV software will allow you to apply this to a composite. I don't want you guys using composites to do this. I want a grayscale image. The reason being is that it's much simpler to understand what's going on and see and learn rather than trying to do it with a color image. So always do this with just one image at a time for now. So the first contrast enhancement technique is known as gray level thresholding. This is where we have this graph, which is called a histogram. And what a histogram is it's got the digital numbers on the bottom, or in our case, it's going to be the physical values. And it goes from 0 to 255 for digital numbers. And then it tells me how many pixels of each individual digital number there are. Now this would be a bar graph, not a line graph, and I think I just previously said something about that. So this is a bar graph where a spectral signature is a line graph. So there are two different kinds of, this is discrete, the other one is a continuous graph. So I draw them as a line graph, and the only reason I do that is because I'm not going to draw out 255 bars. So, so a histogram bar graph shows how many pixels there are for each individual digital number. So we're going to use this for pretty much all of my contrast enhancement techniques. So I take this histogram, and I'm going to apply a threshold. So what's ideal with a threshold is if you have two peaks, and you want to say, hey, what is one peak versus the other? And then you can assign, one becomes black and the other becomes white. And from there, we now have a black and white image. There is absolutely no grayscale. Then we're going to identify between, and sorry, that allows us to identify between those two features. A really good example of this, if you were to use a near infrared band that has, you have water and land in the same image, you're going to see a bump with the water and you're going to see a bump with the land. If you cut it in half, then you're going to see land and water. The second technique is known as level slicing. This is very similar to the gray level thresholding. The only difference is this time around I have two thresholds. So it's great for identifying between multiple peaks. So if you see 3 or more peaks, you might want to use gray level, or sorry, level slicing, not gray level, level slicing. And then you can assign whatever gray values. So here's an example. I try to identify between these 3 peaks. One's going to be black, one's going to be white, and the other one's going to be a gray value in between. So depending on how many gray or levels you have will result in a different image. Do not use more than 11 gray values, because if you exceed 11, it is very hard for somebody to take that 11, like one of those gray values, and move it over to a legend and try to identify what the value is after 11. We can do up to 11, but our eyes just are not capable of doing that. And it makes it very, very hard to read. So again, part of the art side of it, no more than 11. But generally speaking, if we're going to do level slicing, we're only doing 3 or 4 anyways. Then the third type is called a contrast stretch. Now the contrast stretch, it has several like subcategories here. You'll see the different kinds. What this one actually does, instead of just like splitting up the histogram, it actually adjusts the histogram to improve contrast in the way that you want. So it kind of makes a temporary fix to the histogram. You're not going to actually see the values change though. So this is something that I've had students get really confused about, because if you go over a single pixel, it's going to give you a data value. If you do a contrast stretch to it, and it changes in gray color, it's still going to be the same value, right? And it will still represent as the same value. So it just looks different. And that's again the makeup, right? So it's not a transformation, it is an enhancement. So it's just trying to make that pixel look better. So so the first one is a linear stretch. And the whole idea of the linear stretch is really to push out some of the values to the extremes of 0 and 255. So you can see the histogram here. And 0, in this case, there's a bunch more zeros and there's a bunch more 255s. If you see a percentage at the end of the linear stretch, like 2%, that means that 2% of your pixels are going to be black and white. If you see 5%, that means 5% of your pixels are going to be black and white. So linear stretch has all kinds of interesting math that can go with it if you really want to look into it in your textbook. But we're not going to get into that mathematics with it in this class. It's really just a drop-down box in Envy. The next one is a Gaussian stretch. So Gaussian is referring to a Gaussian curve, which is also related to a bell curve. So this one takes all your values and pushes them all up into the middle. And then, so then you have fewer extremes, but more gray values. Sometimes we'll do this for very high contrasty images. So there's just like a lot going on. It's very what we call spatial, like high spatial frequency. So it's just so much going on, and it's just too much. We will actually apply a Gaussian stretch to kind of even it out a little bit and make it easier to look at. Then we have equalization. This one's done quite a bit for like most applications if you're really trying to enhance every single kind of grouping of pixels. So this one, it's equalization, so it is trying to distribute the same number of pixels to each digital number. So if I have my histogram and we're trying to flatten it, so it kind of spreads it out and makes it longer. Or, well, not longer, but spreads it out and makes sure that there's no peaks and that there's an equal number all the way across. Then we also have a logarithmic stretch. This one reduces the zeros and increases the whites, just like as you can see in this picture. The reason we do this one is because it's a very dark image and we want to see more. So this will tend to whitewash something if it doesn't need a logarithmic stretch. So you have to be cautious with it. So that kind of wraps up the third version. So that's the contrast stretching and actually changing the histogram. This next one is all about color. So this is, you see this a lot, and it's not a composite. So a composite is the only way that you can show 3 bands at the same time. You can also show 2 bands at the same time, but you cannot show any more than 3 bands at the same time. It doesn't work. But you can show 1 band at a time using and put it into color using color contrast. So the color contrast is a false color. It doesn't actually work as a natural color, and it only applies to 1 single band at a time. So we do a lot of these with thermal imaging. And so for example, the color table. The color table applies 1 color to every digital number. So that means, for example, if I'm looking at like a thermal image, I'm looking at temperature. So every degree has a different or has a different color. So all those rainbow images that you see for thermal, those aren't actually what they look like when you get them. They're actually black and white. So then they apply a color table to it and make it, oh, look, it's red because it's hot there and it's blue because it's cold. It's actually the reverse. It's like it was actually white for red. Originally, it was white for hot before, and we applied the red to anything that was white. And for black, it was actually for the cold areas, it was black, but we applied the blue. So color contrast and color tables can only be applied to a single band at a time. Then we have the raster color slices. So sometimes it's called raster slices, sometimes it's called color slices, sometimes it's called raster color slices. So depending on the software you're using. This one groups my digital numbers and applies a different color. So as you can see, we've got a part of the histogram. So here's my histogram, and I'm going to make this part purple. I'm going to make this part a light blue, this part green, and it's just that part of it, the digital numbers that's going to be colored that way. This is a really good way if you have a lot of items that you're trying to identify and they seem to have a grouping of values within a certain band. It's a great way to distinguish between things. This can be really helpful with a panchromatic image if you're trying to kind of liven it up. And then you can also control what the range is with the colors, and you can control how many colors and just kind of move forward with that. So the color contrast is only for 1 image. Composites are for 3 images to be put together. So that just brings us to the end of this objective, and in the next video I'll start covering the remaining part of Module 3.